Okay, let's unpack this. Welcome back to the Deep Dives, the show built to deliver the highest quality intellectual shortcuts directly to you. We take a monumental stack of articles, research notes, and historical data, extract the crucial nuggets, and ensure you leave here not just informed, but genuinely surprised.
And today we are turning our gaze toward the heavens to examine the Geminids, a meteor shower that is, without question, the most reliable and prolific celestial show of the entire year.
Right, and while the Geminids are famous for their massive intensity, sometimes spitting out over 200 meteors per hour, our mission today is focused on something far more fundamental. It's the fact that this shower just breaks all the rules of cosmic debris. This deep dive is about extracting the key facts about the Geminids' source, its identity crisis, and understanding why its material is so radically different from every other major shower we track.
Precisely. We are diving into a comprehensive collection of source material here. We've got detailed observational timelines, historical records, and the very latest astrophysical theories right up to 2023. And the foundational fact we have to grasp immediately is that the Geminids, along with the Quadrantids, are one of the only major showers that do not originate from a traditional icy comet.
They come from an asteroid.
An asteroid.
A chunk of dense, rocky material. And that singular distinction, that one fact, changes everything about the physics of the shower, the history of its observation, and our understanding of how cosmic streams even form.
So our mission today is to analyze the source material to really understand the parent body, the Apollo asteroid 3200 Phaethon. We want to scientifically determine why the Geminids have, rightfully earned the spectacular title of the rock comet shower.
Let's start right there with the source of the contradiction. Usually when we talk about meteor showers, think of the Perseids or the Leonids, we are tracking the debris trail left by icy, volatile comets. These comets, they swing near the sun, the ice sublimates, and the escaping gases shed this light, fluffy cloud of dust into space. So, what's up with Phaethon, the parent body of the Geminids?
Phaethon is the core mystery here. Our sources introduce us to 3200 Phaethon, and it's fundamentally classified as an Apollo asteroid.
Meaning it's a near-Earth object whose orbit crosses ours.
Exactly.
Yeah.
But as you said, it shares none of the traditional characteristics of a meteor shower source. It is not an icy, volatile body. It's a dense, rocky object.
And the timeline of its discovery is just fascinating because the shower was known long, long before its source was identified.
Yeah.
When did they actually pin Phaethon down?
So Phaethon was discovered relatively recently, only on October 11th, 1983.
Wow.
And this identification came from the Infrared Astronomical Satellite, or IRAS. Think about that context. The Geminid shower had been reliably observed and tracked since 1862. That's over a century before we had a definitive source.
So that immediately flags Phaethon as unusual. It suggests it was either, hiding really well or only recently became active enough to be recognized as the source.
Exactly. And the sources include this wonderful piece of historical context about the naming. It was attributed to the famous astronomer Fred Whipple.
Right. It's named after the Greek mythological figure Phaethon, the one who drove the sun god Helios's chariot.
And nearly burned the Earth to a crisp when he lost control.
A great story.
And the naming is just incredibly apt because of Phaethon's extreme orbit. While it's a rocky asteroid, it follows this highly elliptical, very comet-like trajectory. Its orbital period is incredibly short, just 1.4 years. And during that period, it swings closer to the sun than any other named asteroid.
So it gets intensely heated.
Intensely, which is why that mythological reference to the sun god's chariot driver who flew too close to the sun is just, it's a perfect touch.
And that tight, high-heat orbit is the key driver of Phaethon's identity crisis, right? It acts like a comet because it sheds debris, but it looks and feels like a rock. So what are the competing theories scientists are using to explain this whole paradox?
Well, they're grappling primarily with two hypotheses. The first is that Phaethon is a dead comet.
A dead comet.
Meaning it was an icy, volatile comet billions of years ago, but after countless passes near the sun, all the ice and volatile material just boiled away, sublimated off, leaving behind a completely desiccated, rocky skeleton.
Okay, so under that theory, the meteor shower debris would have been shed a long, long time ago, maybe when it was still partially active.
Perhaps.
But if it's a dead comet, why is it still producing such a massive, reliable stream now? Over a century after we first observed it. Wouldn't a dead comet have already, exhausted its debris shedding capability?
That's the critical challenge. And it leads us straight to the second hypothesis, which the sources call the rock comet.
The rock comet.
This suggests that Phaethon is not simply an inert skeleton, but a distinct entity that sheds material through non-icy mechanisms. Because it swings so close to the sun, I mean down to 0.14 astronomical units, that's closer than Mercury, it undergoes intense thermal stress.
Okay, so we're talking about thermal fracturing, like a rock cracking from heat. Explain how the heat from the sun could cause a dense rock to shed material without any ice involved.
So when Phaethon approaches perihelion, its closest point to the sun, the side facing the sun heats up incredibly rapidly. We're talking temperatures well over 1,300 degrees Fahrenheit.
That's intense.
And this intense, uneven heating creates enormous thermal stress within the rock structure. Imagine a boulder being flash heated over and over again.
Gang crack.
This differential heating causes thermal fractures, cracks that run right through the rock. Over time, and due to centrifugal forces from its rotation, small, dense fragments, the meteoroids, are literally shed from the surface. This is effectively dust production driven by temperature and stress rather than by ice vaporization. It's a fundamentally different ejection mechanism.
That explanation really clarifies the identity crisis. So whether it's the skeleton of a comet that still has structural weakness or a purely rocky asteroid undergoing thermal fatigue, the crucial point is that the material hitting our atmosphere is just fundamentally different.
Absolutely. And the material composition contrast is the most critical takeaway for you, the listener. We can actually see this difference through spectral analysis.
So.
While traditional comets show a spectral signature that indicates frozen gases and carbonaceous material, Phaethon's spectrum looks like a rocky asteroid. It's likely composed of pyroxenes and olivine minerals that are really common in stony meteorites.
And this mineral composition translates directly into the observable characteristic of the shower.
The extreme density.
The extreme density of the meteoroids.
Indeed. The Geminid meteoroids are significantly denser than typical cometary dust. And if we look at the numbers provided in the source material, this contrast it's just startling.
Okay, let's get into where it gets really interesting. A typical cometary dust flake, the kind that makes up the Perseids, is notoriously porous and light. It floats in at around 0.3 grams per cubic centimeter.
Rank cosmic fluff.
Exactly. And compare that to the Gemid meteoroid density,
which is robustly measured at 2 to 3 grams per cubic centimeter.
That's an order of magnitude difference.
10 times denser.
10 times denser. So what does this phenomenal difference in density mean when that particle hits the top of Earth's atmosphere at tens of thousands of miles per hour?
Oh.
What are the physical consequences for you, the observer?
It means everything. The consequences relate directly to the kinetic energy and then the subsequent ablation or burning up.
Because kinetic energy is tied to mass.
Right. A denser particle, even if it's the same size as a fluffy particle, carries significantly more mass and therefore significantly more kinetic energy.
So the Geminid particle hits the air with a harder punch.
Exactly. When these denser, rocky particles, these are bits of cosmic gravel plow into the atmosphere, they retain that kinetic energy deeper into the air column. They don't decelerate and ablate as quickly as the porous dust.
So they penetrate lower?
Much lower. They compress more air in front of them, and this intense compression leads to higher temperatures and brighter, longer-lasting streaks.
It just fundamentally reshapes the metal picture, doesn't it?
Yeah.
We aren't seeing these delicate, ethereal trails left by sublimating ice remnants.
Not at all.
We are seeing small, dense pieces of rock that have survived intense solar heating, burning up violently deep in our atmosphere.
And that's precisely why the Geminids are known for producing a higher percentage of bright fireballs than most other showers. It's not just about the number of particles, it's about the quality of the particle.
Right.
Their density allows them to burn hotter and deeper, and that results in that spectacular visual display.
We've established that the Geminids are born of rock, but let's talk about their surprising history here on Earth. As we mentioned, their late discovery hints that the stream itself is dynamically young, or at least recently visible to us.
The sources really emphasize this surprising timeline. The Geminids were first observed in 1862.
Which sounds like ancient history to us, but in astronomical terms, it's a flash in the pan.
It really is. We're talking about major recognized showers like the Perseids, which have records dating back to 36 AD.
And the Leonids, known since 902 AD.
Exactly. We have millennium-long records for those streams. So why did the Geminids, which are now the most prolific, only pop up in the mid-19th century?
That's the question.
And it's a critical point that links right back to the density. There are a few astronomical possibilities. One, as you suggested, is that the stream's orbit only recently shifted into Earth's path. But given its incredible density, the favorite explanation relates to the stream's formation and its evolution.
So how does the fact that the debris is rocky rather than fluffy dust influence how quickly the stream becomes visible?
Well, rocky material tends to stick together longer. Fluffy cometary dust, which is driven by solar radiation pressure, spreads out rapidly along the orbit. It forms a broad, diffuse stream relatively quickly.
But dense, rocky meteoroids.
They're less affected by radiation pressure and gravity perturbations. They remain clumped together in a much denser filament for a longer period of time.
So if the stream was formed by a singular event, that dense filament would take much longer to disperse and reach a point where Earth could consistently plow through it and see high numbers. It's like a tightly wound clock spring of debris.
That's a great way to put it. The relative youth of the stream, coupled with its density, points toward a sudden, high-energy formation event, rather than the slow, steady outgassing of a typical comet.
And that leads us directly into the evolving theory of the stream's formation. This is driven by some very, very recent data.
The newest science.
This is where we get into the 2023 research update that ties back to the Parker Solar Probe. This probe is famous for literally flying into the sun's corona, and it gathered data that completely changed the Geminids narrative.
It absolutely did. The 2023 study offered compelling evidence suggesting that the Geminid stream may have formed not from gradual sublimation, but from the catastrophic breakup of a larger parent body.
A violent, highly energetic fragmentation event.
Hmm.
So what specific evidence did the Parker Solar Probe provide to support such a dramatic theory? I mean, it couldn't have seen the breakup event itself.
No, but the probe measured the physical characteristics of the gust particles themselves, deep in the inner solar system, and it found a surprisingly high dispersion velocity of dust away from Phaethon.
What does that mean in simpler terms?
It means the particles weren't just gently falling off, they were being ejected with substantial force. The instruments also measured the specific density gradients and the orbital distribution of these fine particles.
So the dust trail looked less like a passive trail left behind and more like an active explosion site that had recently dispersed material outward.
Precisely. And if we connect this to the bigger picture, the most compelling finding of that research was the orbital connection between Phaethon and two other known asteroids, 2005 UD and 1999 YC.
They are essentially siblings.
They are. The orbital parameters of all three objects align perfectly, suggesting they all share a common point of origin. They were all fragments created by the same massive explosion or shattering event.
And that catastrophic breakup theory it resolves the central paradox.
It does.
But how does this theory reconcile the rock comet identity? I mean, if it was born from a comet, wouldn't it still have some ice?
Well, the theory posits that the original parent body was a massive comet, maybe a giant one. But during one of its early, extremely tight perihelion passages near the sun, the intense thermal shock caused it to fragment catastrophically.
Yeah.
The fragments that survived Phaethon 2005 UD and 1999 YC were the dense, rocky core remnants.
So Phaethon is the largest piece of the skeleton of a giant comet that essentially blew itself apart because it got too close to the sun. And the Geminids are the continuous debris stream from that single violent event, now being replenished by thermal fracturing as Phaethon continues its destructive orbit.
That's the most current and elegant explanation the sources provide. The stream isn't maintained by vaporization. It's maintained by thermal stress and the slow decay of that remnant body. And because the source material is dense rock, the resulting debris stream is a collection of high-density meteoroids, perfectly matching the 2-3 GC-meter measurements we see today.
It elevates the Geminids from being just a reliable annual show to being a dynamic marker of a massive recent celestial explosion that continues to reshape the material flow in our inner solar system.
We are witnessing the aftermath of a cosmic trauma.
Okay, let's pivot from the cosmic history to the practical reality for you, the listener, observation. Given this unique, dense composition, what does the Geminid viewing experience actually look like? How does it translate to what you see in the sky?
It is exceptional, largely due to its dependability and the quality of the individual meteors. The Geminids shower occurs every year, running roughly from December 4th through December 17th.
And the peak intensity is reliably centered on the morning of December 14th.
Right, and the numbers are impressive. Current showers can produce up to 120 to 160 meteors per hour based on the Zenithal hourly rate, or ZHR, under optimal conditions.
The sources also highlight a crucial detail for observers. The highest intensity often peaks around 2.00 or 3.00 local time, regardless of where you are on Earth.
That timing is key. For many Northern Hemisphere observers, the radiant is already high in the sky by local midnight.
Which means you don't have to wait until the deepest, coldest hours before dawn to get peak rates.
Exactly. They put on a show in the mid-evening, which is part of their popular appeal.
Speaking of the radiant, let's explain the shower's name. The meteors appear to radiate from the constellation Gemini, hence the name Geminids, near the star Castor.
And what's fascinating here is that the radiant, that point of origin, is purely a perspective effect. We are moving through a field of parallel debris, and our viewpoint makes those paths converge on a vanishing point in the sky.
Like driving through a snowstorm.
Perfect analogy. If you trace the streaks backwards, they all point toward Gemini.
Wait, so if the radiant is in Gemini, does that mean I should just be looking in that direction?
Absolutely not. That's a common mistake. You should be looking about 30 to 45 degrees away from the radiant.
Why is that?
The meteors seen closest to the radiant will appear short and stubby because they're heading almost directly towards you. The most spectacular long streaks, the ones that travel across a quarter of the sky, are those seen far away from the radiant.
So keep your eyes on the entire sky, but just know that Gemini is the signpost.
That's it.
Now let's get back to the density. How does this rock material affect the speed and the visual signature of the streaking meteor?
So the Geminids are classified as medium-speed meteors. They hit the atmosphere at about 35 kilometers per second, or roughly 22 miles per second.
Which is significantly slower than, say, the Leonids.
Oh yeah, the Leonids approach at over 70 kilometers. They're speed demons.
And that slower speed is a huge benefit for you as the viewer, right? It makes them fairly easy to spot, as the sources mentioned. You get a slightly longer moment to register the streak and watch its trajectory.
But the truly distinct visual signature is twofold: color and ablation depth. The sources note that Geminids often appear yellowish in hue. This yellow color is a direct consequence of the dense mineral composition.
Why yellow? What's burning up to make that color?
As the rocky material ablates, it heats trace metals within the meteoroid. The yellowish-orange color we observe is typically associated with the atomic emission lines of elements like sodium, which is common in stony meteorites.
And because the particles are denser, they burn hotter.
These colors are often more pronounced than the fainter traces seen in pure dust.
And the ablation depth is also distinct, right? Where do these rocky bits usually disintegrate?
They penetrate much lower than typical cometary fluff. The Geminids usually fall apart at heights above 24 miles, or 39 kilometers. Fluffier meteors can vaporize way higher up, sometimes above 60 miles.
So that lower altitude means the streaks often appear brighter and closer to the horizon, which contributes to their fireball reputation.
Exactly. This combination of medium speed, intense yellowish color, and low ablation depth makes a Geminid easily distinguishable from other shower types.
Finally, let's look at geographic visibility, which is important for tailoring the experience for everyone listening.
Your location on Earth significantly impacts the visible rate. For observers in the Northern Hemisphere, conditions are superb.
Why is that?
The radiant rises near sunset and reaches its peak elevation early in the morning. This means the radiant is often usable for 8 to 10 hours during the night, leading to consistently higher visible rates.
And if you're listening from the Southern Hemisphere?
Down south, the Geminid radiant is never as high in the sky. It only appears around local midnight or later, and it generally stays pretty low above the northern horizon.
So you'll still see some.
Oh, you will still see Geminids, but your total count will be significantly lower than the theoretical ZHR maximum because you are viewing the stream at a much shallower angle, and the atmosphere obscures fainter meteors near the horizon.
So it's a great show, but the Northern Hemisphere definitely wins the visibility contest for this particular shower.
No question.
Now we move into the serious analysis, the data dive.
Yeah.
We have this detailed historical timeline of the Geminids from 2006 right up through the forecasts for 2025. It charts the recorded zenithal hourly rate maximums, or ZHRs. In this data, it shows the immense reliability of the Geminids, but it also reveals critical information about the structure of Phaethon's debris stream.
The value of this data is not just in the high numbers, but in showing the shower's consistency. While the standard quoted maximum is, 120, 160 per hour, the timeline proves the stream frequently delivers far more.
Let's pick out some of the high points that demonstrate the stream's density. The sources show 2007 hitting 170 ZHR.
2011 was incredibly strong, reaching 193 ZHR.
And the true standout year was 2015, which hit an astronomical maximum ZHR of 203.
A ZHR of 203. That means that under absolutely perfect, cloudless, moonless skies, an observer would see over 3 meteors per minute looking straight up.
That's staggering.
That number underscores the vast amount of rocky debris 3,200 Phaethon has deposited. It also suggests that the debris is not uniformly spread out, but organized into dense filaments or clumps.
Right. If the stream were perfectly uniform, the ZHR would be consistent year after year, varying only because of the moon. But the variability from 114 ZHR in 2008 to 203 ZHR in 2015 tells us the Earth is punching through different parts of the stream each year.
That's the key analytical point, and this is where the lunar phase data included in the timeline becomes so crucial. It allows us to filter out the influence of the moon and focus purely on the stream's structure and density variations.
You can have a dense filament, but if the moon is full, you just won't see it all.
Exactly.
So let's use the timeline to analyze the dampening effect of the moon, which is the #1 variable for the practical observer. We can compare the bad lunar years.
Let's look at 2016. The moon was at 100% a completely full moon, maximum light pollution.
You'd expect a terrible show.
You would. Yet the Geminids still managed a recorded ZHR of 157.
That is an incredibly powerful showing. It demonstrates that the stream was exceptionally dense that year. Even a full moon couldn't completely obscure the brilliance of that filament.
Exactly. But now, here's the complex part that needs a deep explanation. Compare that 2016 result to 2008.
Okay, 2008. The moon was also near full at 95%, but the recorded ZHR maximum was only 114.
Right. So why the dramatic difference between two full moon years? 157 versus 114.
It must be the stream itself.
This contrast is the evidence of the stream's clumpy structure. In 2016, Earth was perfectly timed to pass through a highly concentrated, very dense filament of debris. Even with the lunar glare, enough bright meteors survived the light pollution to yield a high ZHR.
So the ZHR of 157 in 2016, despite the full moon, indicates that if the moon had been absent, that year would have likely been well over 200 ZHR, maybe even higher than 2015.
That's the interpretation. And conversely, in 2008, even though the moon was only marginally less bright, the Earth likely encountered a more dispersed, less dense part of the stream.
And when the stream is thinner?
Fewer bright fireballs are produced, and the moonlight just washes out the bulk of the fainter meteors, resulting in that much lower visible rate of 114. The data shows the orbital position matters just as much as the lunar phase.
So now let's contrast that with the optimal viewing years, when the moon was nearly absent, allowing you to see the full range of brightness.
These are the glory years. Consider 2009. The moon was a mere 9% new moon. That year achieved 140 ZHR, perfect dark conditions.
And 2012?
2012 featured a 2% new moon, almost invisible, achieving 134 ZHR. What these low moon numbers prove is that while the raw ZHR might be slightly lower than a spectacular filament year like 2015, the quality of viewing is maximized. You can pick up the faintest, most numerous meteors.
It's the difference between seeing a few bright fireballs versus seeing the complete texture of the debris stream. So if you're planning your viewing, you should prioritize a dark moon over a theoretical high ZHR.
Absolutely. Low moonlight transforms a great shower into an unforgettable one. And looking ahead, the timeline gives us some promising forecasts.
2024 is projected for a 112 ZHR, but
it's badly hampered by a 99% waxing gibbous moon, almost full. We know from the 2008 data that visibility will be strongly suppressed, making 2024 pretty challenging.
But the forecast for 2025 looks exceptionally good.
Very good.
We're looking at a high projected ZHR of 150, and the moon is predicted to be a favorable 26% waning crescent.
That is a near-perfect combination of a high peak rate and low lunar interference. Analyzing this detailed data just reinforces the Geminids' premier position among annual showers. It also provides a map of the stream itself, showing us where the dense filaments are and how the orbit of Phaethon dictates our viewing experience.
We've covered extensive ground today, examining why the Geminids are so fundamentally unlike their cometary cousins. We move from the high-density physics of Phaethon to the implications of recent catastrophic breakup research. Let's bring it all back to the essential takeaways for you.
The first key takeaway has to be the unique origin story. The Geminids are not soft, fluffy debris. They are dense, rock-like particles, 10 times heavier than typical cometary dust. Their parent is the Apollo asteroid 3200 Phaethon, which is now considered either a heavily damaged dead comet or a distinct rock comet shedding material through intense solar heating and thermal fracturing.
Secondly, remember the observation characteristics driven by that density. The meteors are medium speed, about 35 kilometers, allowing you longer to track them. Their high mineral content causes them to often appear yellowish in hue, and they penetrate lower into the atmosphere, leading to a higher frequency of bright fireballs.
And finally, the stream is highly prolific and dynamically young. Its light discovery in 1862 and its extreme ZHR variability reaching peaks of over 200 per hour suggests the Earth is interacting with dense, clumpy filaments of debris. Debris created by a violent, catastrophic breakup event involving Phaethon and its siblings, 2005 UD and 1999 YC, is recently confirmed by that Parker Solar Probe data.
And this raises an important question that the sources strongly imply. Given that Phaethon continues its destructive, tight 1.4-year orbit, constantly being stressed and fractured by the sun, how will the Geminids stream evolve in the coming centuries?
Well, the catastrophic breakup theory from 2023 means the stream is still settling down from a massive explosion. As Phaethon continues to shed material violently through thermal means, the dense stream we see today will likely continue to be one of the most visible for centuries. But the specific filaments and peak ZHRs might shift dramatically as its orbit subtly changes and the remnants of the explosion disperse. We are watching a celestial event that is still, in a sense, in motion.
Next December, when you spot a brilliant yellowish flash streaking across the night sky, remember you're seeing the debris of a rocky skeleton that defies celestial categorization, propelled by thermal stress, not ice.
Look up and enjoy the ongoing aftermath of a cosmic catastrophe.
That's all for this deep dive. We'll see you next time.